So greetings to doctors and my friends. Today we are going to present about the application of X-ray for fluorescence. So before we start our present today, we would like to introduce ourselves first. My name is Chayasin with matrix numbers S34113.
My name is Chua Zixuan with number matrix S341117.
My name is Nur Shakira binti Muhammad with matrix number S34178.
My name is Anissa binti Saimi with matrix number S34110.
So let us proceed to next slides. So as you can see, this is the topics of presentations for our presentations today. So I would like to start the presentation with what is X-ray fluorescence. So X-ray fluorescence is an X-ray instrument which used to analyze the chemical compositions of raw materials. And it works by exposing the sample to X-ray and measuring the characteristic of fluorescence radiations emitted by the elements present in the samples. So it is suitable for bulk analysis of a variety of materials because it can perform a powerful and convenient non-destructive multi-element techniques. So this is the sample collections and preparations that used in the instruments. So the first part will be the solid. Solid sample can be in fine powder form or being cut and polished to a perfectly flat surface or pressed into a pellet. While in a liquid form, liquid need to prepare by pouring into plastic sample cup and choosing a perfect support forms that provides a balance of strengths and transmissions capabilities and contaminations. So that is the example of types of XRF films. I would like to pass the presentations to Chua for the following explanations.
Thank you, Chai. So now I will explain about why solvent use should be contain element with low atomic number Z. For if we use low atomic number elements such as chlorine, argon, potassium, and calcium, it will give us only K peaks. L peaks from these elements are too low energy. These are not transmitted and not detected with conventional silicon-based detector. While for the high atomic number elements such as barium, mercury, lead, and uranium will give a L line. Well, for the K peaks for these high Z element are too high in element, these electrons have high binding energy and cannot be removed with the limited voltage available in field portable analyzer, while for the middle atomic number such as rhodium may give us both K and L line. So as you can see from this picture, an ejected electron from an atom in the K cell caused by a primary excitation X-ray, the vacancy is filled by an electron field from another shell which emit a secondary fluorescent X-ray. So now I will explain about the intensity fluorescence used for quantitative analysis. The intensity of fluorescent X-ray depends on how much of element A in the sample content. The intensity of the fluorescent X-ray of element A will be higher as more element A was contained in the sample. It can be done in reverse if the fluorescent X-ray intensity and concentration of an element content in a sample are known. Allow us to know how much of element was contained in another sample by its fluorescent X-ray intensity. There is two methods can be used to measure the concentration of the X-ray fluorescence by using the calibration curve, measuring several samples of non-element concentration by finding relationship between intensity of the measured element's fluorescent X-ray and the concentration. We can obtain the element concentration of unknown sample from its X-ray intensity. Well, for the second method, which is fundamental parameter method of theoretical calculation by derive the intensity of the fluorescent X-ray is the type and property of all elements that compose a sample are known. The composition of unknown sample can be extrapolated by the fluorescent X-ray intensity of each element. The formula that can be used to find the concentration of the X-ray fluorescence is C equals to K times I times M times X, where the C is the concentration of the element, K is the operating condition and is a function of the spectrometer, I is the intensity of the measured signal, and the M is the inter-element effect. The last one is S, which is specimen homogeneity. So now I will pass the further presentation to the next partner.
Thank you, Joa. Okay, I will continue for external and external standard. For internal standard, the internal standard consists of an element not present in the sample. Internal standard concentrations should be somewhere in the medium concentration range of all elements to be determined, which is the internal standard is a non-concentration. Most commonly used internal standard elements are gallium and yttrium, as both elements typically do not interfere with elements to be determined in the sample. For external standard are separate sample and a reference material with one concentration of elements. External standard used to create a calibration curve. They are not present in the sample being tested. Example of external standard include certified reference material or other well-characterized sample with non-elemental composition. So, how internal standard can improve the precision of fluorescent X-ray? The first one is by metric correction. Metric correction correct the variation in sample composition and metric aspect. Sample metric can influence X-ray fluorescence signal. The second one is drift compensation. Drift compensation provides reference point within each sample, allowing for detection and correction of instrumental drift in fluorescent X-ray. The third is normalization of signal intensity. Reference for signal intensity, factors like size of sample or instrument setting can be identified for improving precision. The last one is calibration improvement. Internal standard used in conjunction with external standard to calibrate the instrument. It can establish relationship between signal and actual concentration. So I will pass the next presentation to my friend.
Thank you, Shakira. Next, I would like to explain about why particle size distributions of standard should be similar to that of unknown analyte. First, the absorption and scattering effects. When standard closely match the particle size distribution of the unknown analyte, these effects are more consistent. The second one is the matrix effect. Using standard with a similar size particles distribution helps for matrix effect. The third one is homogeneity and representativeness, enhances the homogeneity of the calibration curve, allowing for better extrapolations of results to the analyte. And lastly, avoiding bias in calibration. Standard significantly deviate in particle size from the unknown analyte. The calibration may introduce bias. Next, analysis of X-ray fluorescence applications. The first one is for metal analysis. Highly reliable thermoscientific XRF spectrometers can be used to analyze the trace to percent element concentration levels of raw materials, slags, alloys, and coatings with accuracy and precision. The second one is for analysis of cement. Thermoscientific combined XRF, SRD spectrometer can be used to perform essential screening of incoming raw materials for the cement making process, and they are also used to continuously monitor the compositions of raw mill blends and clinkers to prevent process disruption and obtain suitable cement and products. And then for analysis of geology and mineral analysis, thermoscientific SRF spectrometers can help researchers understand the value of mineralogical samples by providing the precise elemental analysis required to quantify both economically important and undesirable compounds. And for analysis of petrochemicals, thermoscientific SRF instruments can be used to screen crudes and refined oil to guarantee optimal product quality and regulatory compliance. Next, for analysis of polymers, an essential component in the plastic manufacturing chains, providing insights into additive concentration at the parts per million ppm range. And for the analysis of glass and ceramics, thermoscientific SRF solutions, particularly wavelength dispersed X-ray fluorescence WDXRF, are used to guarantee that each individual ingredient is accounted for with the precise elemental percentage needed to create the desired final product. And for wood analysis, it's reliable and effective method for verifying the compositions of wood treatment products and treated timber. And lastly, for analysis of textile, monitoring elemental composition and detect impurities or variation in raw materials, ensuring the consistency of the final textile products. So that's all from us. Thank you.